This lesson is going to cover dilution and then some solution stoichiometry. We often will store solutions as concentrated stock solutions. The point of that is then it's in a smaller volume and can be in a smaller bottle and is easier to store. Then when you want to make a solution of lower concentration from the stock solution, you add more solvent. So your amount of solute isn't going to change, just the volume of the solution. The central equation for doing this is M1V1 equals M2V2. I always like to emphasize that this is an extremely important equation. You will use it throughout this course, and if you go on in chemistry or biology, you are going to run across M1V1 equals M2V2 all the time. I use this equation almost on a daily basis in graduate school. So, very important equation. You need to understand how to use it. So, let's talk through how we're going to use it. So, let's see. M1, V1. So, the molarity of your initial solution times the volume of your initial solution is equal to the molarity of your second solution times the volume of your second solution. So what you need to do is figure out which molarity and volumes go together. Here's a sample question. To what volume should you dilute 0.2 liters of 15 molar sodium hydroxide to make 3 molar sodium hydroxide? So here we know that we have a molarity of 15 molar. Our volume of that solution is 0.200 liters. We know we want our final volume to be, our final molarity to be 3 molar. We don't know our V2. So what we're going to do is simply plug in the numbers. 15.0 times 0.200 is equal to 3 times V2. Then we can solve for V2 and get the answer of 1.00 liters. So what that tells me is in order to get my molarity down to 3 molar, I need to bring my final volume up to 1 liter, which means I'm probably adding about 800 milliliters of water. So remember, V2 is final volume, not volume of water that you're adding to it. Here's this worked out again. You found your M1, V1, M2, and then you can solve for V2. Right, another question. What is the concentration of a solution prepared by diluting 45 milliliters of 8.25 molar nitric acid to 135 milliliters? So again, M1, V1 equals M2, V2. Here we know our M1 is 8.25 molar. Our V1 is 45 milliliters. Our M2, we don't know. And our V2 is 135 milliliters. Now notice I'm using this just in milliliters. I did not convert over to liters. The nice thing about this equation is it does not matter what units you're in as long as they're the same at the beginning and the end. So here I'm in molarity. I could be in some other unit of concentration. This equation would still work. Liters, milliliters, doesn't matter as long as both are in the same. So here 8.25 times 45.0 is equal to M2 times 135.0. So I can find that my M2 is 2.75 molar. Here's another example. You will probably want to pause and make sure that you can do this on your own. How would you prepare 200 milliliters of a 0.25 molar sodium chloride solution from a 2 molar solution? So M1V1, M2V2, so 0.25 molar times 200 milliliters is equal to 2 times V2. Solve for my V2, and I get 25 milliliters. And then the question is actually, how would you prepare? So you're going to take 25 milliliters of the 2 molar solution and add water so that the final volume is 200 milliliters. So you're actually adding 175 milliliters of water to make your final solution. All right, we can also, because molarity relates moles to liters, we can use it in chemical reaction stoichiometry as well. So we don't have to go from grams to moles to moles to grams. We can go from volume to moles to moles to volume, assuming we know molarities of things. So for example, what volume of 0.150 molar potassium chloride is required to completely react with 1.50 liters of 0.175 molar lead 2 nitrate in the following reaction? So here we are going from volume. So I would go from volume of the lead 2 nitrate to moles of lead 2 nitrate, and then moles of lead 2 nitrate over to moles of potassium chloride, then moles of potassium chloride to volume. So let's talk that out. So I'm going to start here with my 0.150 liters of my lead 2 nitrate times my molarity. I know that 1 liter of that is 0.175 moles of my lead compound. Then I'm going to convert from my lead compound over to my potassium chloride using my balanced equation. So 1 mole of my lead compound gets me 2 moles of KCl. And then I know that my KCl is 0.150 moles in 1 liter from this. So I can do all of that math and find out what volume I'll end up in liters. And my answer ends up being 0.350 milliliters. Not milliliters, liters. Liters of my KCl. So you can see, again, thinking through this kind of problem, you want to start with what you know that only has 1 unit associated with it, that you can then convert to find what you're looking for. So here we're converting liters to moles to liters. And there's another way of thinking it through with the flow chart in there. Here's another example. Again, I would recommend pausing and working this through on your own. 43.8 milliliters of a 0.107 molar hydrochloric acid is needed to neutralize 37.6 milliliters of a barium hydroxide solution. What is the molarity of the base? So here we are starting with our milliliters to moles of hydrochloric acid. So 43.8 milliliters, and then you can convert from milliliters over to liters. And then 1 liter is 0.107 moles HCl. Then from my balanced equation, I can see that I have 2 moles of HCl for 1 mole barium hydroxide. Oops. And then that gets me how many moles of barium hydroxide. So actually just want to solve it right there. And that gets me 0.000234 moles of barium hydroxide. And then I want to find my molarity, so I'm going to take my moles, divide by my liters, in this case 0.0376 liters, and that will get me my molarity, which is 0.0623 molar. So that last bit involved 2 steps. I had to solve for my moles, and then once I had moles, I could divide by my liters to get to molarity. I can get there all in one step just by dividing, but I think it makes more sense to do it in 2.